Welcome, good to see you. Today we're going to begin transitioning from how our programs interact with hardware to how they interact with software, in particular system software. And we're going to start that investigation by studying and learning about a process called linking, which is how the system builds your programs. Okay. So we're going to study the process of linking, and then I'm going to show you a really cool technique called library interpositioning, which allows you to use linking to actually intercept on function calls in libraries like the standard C library. So it's a very, very powerful and interesting technique, and it's all enabled by linking. So let's start with a simple program. This program consists of two modules, main.c and sum.c. Sum.c takes as an array as an argument and a length, n, and then it sums up the elements of that array and returns the sum back to the caller. Main.c calls the sum function using and passes it a two-element array of ints, and then returns the value received from sum. That's kind of an odd thing to do, to return your exit status like that, but we just did it so that the compiler wouldn't optimize away all of our code. All right, now let's look at what happens when we want to compile those two modules. For each of main.c and sum.c, the GCC calls a series of translators on those modules, on those .c files. First calls the C preprocessor, CPP. Then it calls the compiler, the actual compiler, which is CC1. The compiler generates assembly, which is then translated by the assembler, AS, resulting in a .o file called main.o. Similar things happens for sum.c. So after these three translators work on the code, we have two object files, two .o files. The linker takes those .o files and puts them, links them together, sort of smashes them together to form a single executable called that we can then run, that we can then load and run on the system. So the main.c and sum.c are called source files. These .o files are object files that we were separately compiled, but and we call them relocatable object files because they can be combined together to form the fully linked executable object file. So why do we do it like this? Why do we allow this so-called separate compilation? Why don't we just have like one big file with all of our code in it? Well, there's a couple reasons. The first is modularity. So by allowing you to break your code into smaller pieces, you can put related functions into separate source files. You can define libraries of functions. So it's just good technique, and it allows you to kind of break your code up into nice modular pieces. The other reason is efficiency. So if we've broken up our program into multiple chunks, if we change, and if we only need to change one of the chunks, we don't have to recompile all the other modules, right? We can just recompile the one module that we changed and then link them all together again, right? So it's efficient in time. It's also efficient in space because you can take all of the functions in the standard C library. You could put them all together, but then the only functions that you actually get compiled and linked into your program are the ones that you actually call. Okay, so you can you can save space. You don't, normally you use only a small subset of the standard C functions, and so there's no point in linking all of those functions into your code if you don't need them. All right, so what do linkers do? Well, there's two main tasks that a linker performs. The first is called symbol resolution. So programs define and reference symbols, okay, what the linker refers to as symbols. And these are global variables and functions, okay, and the names, and those objects are referred to as symbols. So here we're defining a symbol called swap. Here when we call swap, we're referring to that symbol. Okay, that's a reference to the symbol. And here we're defining a pointer to an int called xp. So we're defining xp, and we're initializing it to the address of x. So that's a reference to x. Okay. So the symbol definitions are stored in the object file by the assembler in a symbol table, which is an array of structs, where each struct contains information about the symbol, like the name of the symbol, its size, and where it's located. Okay. Now, what we mean by symbol resolution is that during the linking process, the linker associates each symbol reference with exactly one symbol definition. Okay. So it's possible in multiple, why is this an issue? Well, it's possible, like in multiple modules, you may declare a global variable with the same name. The linker has to decide which one of those definitions to use for all subsequent references. Now, once the linker is associated a unique object with a unique symbol definition with each reference, then it does the second step, which is relocation. And during relocation, it merges all of the modules together into a single executable object module that can be directly loaded and executed on the system. So when it does this merging, it has to figure out where each symbol, each function, and each variable is going to be stored. Okay, and this is called relocation because initially functions are just stored at some offset in their object module, right? Because the linker doesn't know where those functions are actually going to be eventually loaded into memory. So before relocation, the address of a function in the object module is just its offset in the module, and similarly for data. During the relocation step, the linker decides on where each symbol is going to be ultimately located in memory when the program executes, and it binds those absolute memory locations to the symbol, and then it goes and looks at all the references to those symbols, and it updates those references so that now they point to the correct address. Okay, so figure out where stuff is going to go. For each definition, figure out where it's going to go, and for each reference, then update that reference so it now points to the right spot. So let's look at how these steps work in more detail. Before that, we need to define a few things. So there's three kinds of object modules that I've alluded to. There's the .o file, which is a relocatable object module. This is the output of the assembler. Okay, and it's a binary file, but it's not in any form that can be directly loaded into memory. It needs to be manipulated by the linker before it can be actually used. There's the executable object file, which is generated by the linker. These are called a.out files sometimes. Historically, the very first Linux systems, the executable, this sort of the default name that the the developers of Unix used, the default name for their executables was a.out. So that's just sort of a historical reason that it's called a.out. And then there's another type of object file called a shared object file, or .so file, which is a sort of a modern technique for creating shared libraries. And we'll look at those. We'll look at those later today. Now, object modules come in a standard format called ELF format. And it's a unified format for .o files, for executables, and for .so files. They all use the same format, the same general format. So while these ELF binaries they're binaries, they're very structured, okay? And they're broken up into sections. At the beginning is a header that defines things like the size of the words, the byte ordering, whether it's a .o, an a.out, or a .so. So it just provides some sort of general information about this binary. And then there's what's a so-called segment header table, which it's only defined for the executable object files, and it indicates where all the different segments of the code are going to go in memory. So where does your stack go? Where do your shared libraries go? Where does your initialized and uninitialized data? Where does your code go? Right. So all these various sections are defined in the segment header table. And then there's the code itself, which is called the .text section for sort of arcane historical reasons. So .text is always code. And then that's followed by read-only data, such as the jump tables in switch statements. So text and read-only, the .text and .ro data have the property that they're both read-only. You don't write to them. Okay. Then that's followed by the data section, which contains space for all of your initialized global variables. And then there's a section called BSS, which defines the uninitialized global variables. Now, this doesn't actually take up any space because they're uninitialized, right? Okay, but there are entries in the symbol table for them, and when this program gets loaded, these variables are going to need, they're actually going to have space allocated for them. BSS is another one of those sort of arcane names. It goes all the way back to the 60s, where there was an IBM instruction called the block started by symbol. I think a better way to remember what it means is better save space. Okay, so you can, if you have a separate section for the uninitialized variables, since they're not uninitialized, they don't have to consume any room in the .o file. Okay, there's also a section for the symbol table. This contains, like I said, it's an array of structs for procedures, global variables, and anything defined with the static attribute. And each one of these symbols gets an entry in the symbol table. And then there's two sections called that contain relocation info. So this is the notes. When the linker went and identified all the references to symbols, it put a little note to say, I'm going to have to remember to fix the reference to this symbol up when I actually create the executable. So a relocation entry is just like a note that the linker, or that it's a note that the assembler makes to the linker to say, hey, you're going to have to fix up this reference because I don't know where this symbol is actually going to be stored in memory when it's loaded. Okay, and then there's a debug section that contains information that relates line numbers to in the source code to line numbers in the machine code. Okay, and so this is called .debug, and this is what you get when you compile with -G. And then there's a header table that tells you where all these different sections start. Now, to a linker, there's three different kinds of symbols. Global symbols are defined in some module M, and they can be used by other modules. Right? So, I mean, did you notice if we have a program that consists of multiple modules, and we compile each one of those modules into a .o file, we'll be calling functions that are defined by other modules. Right? Okay, so those, but there's no error. The compiler doesn't throw an error because it's assuming that those are defined in other modules, and it assumes the linker will be able to find them and determine the address. So anything that's defined with any global, either global variable or function name that's defined without the static attribute is a global symbol. Okay. Now, and then external symbols are kind of the flip side of that. External symbols are symbols that are referenced by some module but defined in some other module. Okay, so in our little running example, when main.c called the function sum, it was referencing an external symbol. Okay, and then there's local symbols, and these are symbols that are defined and referenced within a module. Okay, and those you create. This is different from local variables. Okay, the linker, local C variables are managed by the compiler on the stack. Linker has no idea about local C variables. Okay, in this context, when we talk about a local symbol, what we're talking about is either a global variable or function declared with the static attribute that can only be referenced from within that module. So we say that the scope of a function or a global variable defined with the static attribute is limited to the module that it was defined in. Okay. So this is, in C, this is how we do abstraction. And this is how we can create sort of private functions and private functions that can't be called from outside that module. Okay. So for instance, if we want to make a library in C of functions, we want to make a collection of functions that other programs can then call, link into their program and call. The functions that we want to make visible to other programs are defined without the static attribute. And the functions that we want to have private and just be internal, we declare with the static attribute. Okay. And that way we get abstraction and we get hiding, information hiding, and we're only exposing data and functions that we want to expose. All right, so let's look in detail how this symbol resolution step works. Recall our example program. So here we're referencing a global called array that's defined within main.c. Here we're defining main, a global called main. Here we're referencing a global called sum that's defined in sum.c. And val is a local C variable on the stack, and linker knows nothing about that. Okay. Nor does it know anything about I or S, which are also local variables. Now let's just let's make sure that we understand the difference between local static C variables versus local non-static C variables. So here we're defining a local static variable called int within this function f. Now, because it's local, its scope is limited to this function. So this variable x can only be referenced within function f. And similarly for this definition of x in function g can only be referenced by function g. Now but because it's declared with the static attribute, it's not stored on the stack. It's actually stored in dot data, just like a global would be. So it's like a global in the sense that it's actually stored in dot data rather than the stack. But it's like a local C variable in the sense that its scope is limited just to the function that it's defined in. Okay, so what the compiler will do, it'll allocate space for each definition of x. So this, and it'll give it some name to disambiguate it. So maybe it will call this one x.1 and maybe this one x.2. So these symbols are allocated in dot data because they're initialized, and they get symbol table entries just like any other symbol. Okay, so I said that during symbol resolution, the linker associates each symbol reference to exactly one unique symbol definition. Now, how does it do that if there's multiple symbol definitions across all the modules? So, to understand this, we'll define symbols as being either strong or weak. So strong symbols are either procedures or function names or initialized global variables. Weak symbols are uninitialized global variables. Okay, so int foo here is a strong symbol because it's initialized. We're initializing it. P1 is strong by definition. Foo is weak in P2.c. This definition of foo is weak because it's uninitialized, and the definition of P2 is strong. Okay, so that the rules that the linker uses are the following. Multiple strong symbols not allowed, so that's an error. Okay. So that means that if across multiple modules we declare a function with the same name, the linker will throw an error. That's not allowed. Given a strong symbol and multiple weak symbols, the linker will always choose the strong symbol. Now remember, if we initialize a global variable, and if we declare an initialized global variable across multiple modules, that's an error because those are strong symbols, okay, by rule 1. But if we have one strong symbol and multiple weak symbols, all with the same name, then the compiler will choose the strong symbol. Okay. And it will associate all references to that symbol will go to that strong symbol. And if there's multiple weak symbols, then it just picks an arbitrary one. And this, as we'll see, can be problematic. Now you can override it with this GCC flag called no common. And if you declare your function with this no common argument, then multiple weak symbols will throw an error in the linker. All right, so why do we care about all this stuff? Well, it turns out if you're not aware of this stuff, you can run into some really serious problems that are just perplexing and confounding. Right? So linker errors are like the worst kind. They're the hardest kind to debug because people aren't usually aware of what's going on inside their linkers. And usually it's only like the very best programmers that really understand how these linkers work and what kind of errors they can throw and how to debug them. So let me show you some examples of these kind of errors. All right, so we have a program. We have two modules, so each of these rectangles corresponds to a module. And we're defining P1 in each module. So that's two strong symbols. That's an error. Okay. Now here we're defining P1 and P2, so we're okay. But now we've got two weak symbols. Both are integers, variables called x. So, and if these modules are referencing x, the linker will just pick one of these to serve as the definition. But is this really what you want? Now, in this case, it doesn't really hurt anything because x is declared in both modules as an int. Right? So it'll just be some integer-sized variable that, and it'll be somewhere in, but it doesn't really matter which one the linker chooses. But we start to get into trouble if we declare these weak symbols with different types. So here we've declared an int x in one module and a double x in another module. So if we write to x, if the linker just arbitrarily chooses this symbol definition to use, now this is a symbol that of length 8, of size 8. If we, anywhere in this program, if the linker chooses that, then anywhere in the program, those references to x will be to this double word. Even in this module, if we reference x, it'll be an 8-byte write. So it'll overwrite y with the high order. Excuse me? Oh no, it's completely. It'll just pick one arbitrarily, and you don't know. I mean, All right, here's a problem. We've defined a strong symbol x because we've initialized it. So the linker will associate all references to x to this integer-sized symbol. So if we write oh yeah, right. So writes to x here. This will be a double in this module, but it'll overwrite y in this module. So that's really nasty. And here we're defining a strong symbol x. So references to x in this second module will always it will refer to this initialized variable, which might not, so it might not be what you want, right? You may be assuming that it's uninitialized in your code. Okay, and then you get the ultimate nightmare scenario. Suppose, because we're following a standard ABI, we can compile our code with multiple compilers. And this actually happens in some, oh yes, questions?
Oh, well, just on the second to last one, if you write to x and p2, wouldn't the strong x and p1 still take preference?
Oh yeah, actually you're right. It will still take preference, and you'll be writing a 4-byte quantity, which is what you want. So that slide's not quite right. So that.
And then I have a quick question about something before. Oh yeah, well, what is the point of doing the static versus non-static if it's always being referenced just locally in your function anyway? What is the point of declaring it static? Is it stores it in the...
No. It's if you reference a variable that's, you mean, so a variable that's defined in your module, and then you
defined locally within your function, like in the previous example.
With the static.
Right, with the static versus non-static. But
right.
They're both local variables anyway.
Oh, they're both local. So you do this if you want a value to retain from. If you want that variable to retain value from invocation to invocation. So suppose it's usually a bad idea, as we'll see when we study threads, because it makes your code non-thread safe. But early random number generators would compute a pseudo-random number, and then it would store it in a static variable, and then use that as the the starting value for the next time you call that function. So whenever you want values to persist across function invocations, you would do static. Yes?
So how does we try to write a double in the second to last one? Like something with length double. Will it crash or?
Well, wait a minute. Let me get this straight. Writes to x in P2 will actually correspond to the memory it'll actually go to the memory location. I'm sorry, I need to amend that. So writes to x in P2 will be 8 bytes because the compiler knows that it's a double. But it'll go to a memory location that's only 4 bytes because the linker chose the strong symbol. Okay, so the writes to x in P2 will actually overwrite y. Okay. I'm sorry. Yes, question.
How do you know that x and y are in like contiguous spots in memory? Like they're on top, they're beside each other on the stack?
That's just usually the way it happens.
So declaring two global variables puts the variables on the stack.
No. Global variables go in .data. They don't go on the stack. But usually if you define local variables in a function, it will allocate them one after the other on the stack. Okay. All right, so all this discussion about these weird strong weak symbol rules that the linker have, it's another reason to avoid global variables if you can. If you need to declare a global, see if you can declare it static because that'll limit its scope to the module that it's declared in. So that's a good idea if you can do it. And if you define a global variable, initialize it so that you'll discover if you have multiple initialized global symbols with the same name in your code. And then if you want to, it's always good practice if you're referencing an external variable to tell the compiler about it by using the extern attribute. All right. So now, at this point, the linker has associated every symbol reference with some symbol definition. Now it has to take all those relocatable object files and smush them together and create like one big executable. So suppose with our example, our little running example, each main.o and sum.o contain code and initialized data. Sum.o doesn't have any initialized data, it just has code. And then there's system code that actually runs before and after your program. So when your program runs, it actually starts executing startup code from libc that sort of initializes things. And then the last thing that it does is it calls main and passes it argc and argv. Okay. And then when your program exits, well, that's a syscall. But if your main function routine does a return, then it returns back to that startup code, which then does an exit. Okay. So this is just, and so this consists of text and data as well. And so when the linker relocates these object files, it takes all of the code, the .text sections from each of the modules and puts them together contiguously in the .text section for the executable object file. Okay, so it just puts them together in some order that it determines, and it creates a combined .text section in the executable that contains all of the system code and all of the code defined in the modules. And then it does the same thing with the data. It takes all the .data sections from the various object files and puts them together in one combined .data section in the executable. And it also merges the symbol tables and the debug information as well. Now, just the act of sort of relocating these object files requires the linker to figure out where it's going to actually store these different symbols when this program gets loaded. So it has to pick an address for main that function will start at, some absolute address. It's going to have to do the same for swap. So for all the data arrays, right? But the problem is that when this code is compiled, the compiler doesn't know what addresses the linker is going to pick. So the compiler creates these reminders to the linker called relocation entries, which are then stored in the relocation sections of the object file. And these relocation entries are instructions to the linker that there's a reference to a symbol that's going to have to be patched up when the code is actually relocated and merged into the executable. So let's look at a couple of examples. So in our main.c module, there was a reference to this global symbol called array. Okay. And then there's also a reference to this global symbol sum, which is a function. So the compiler creates two relocation entries. The first one for the reference to the array A. So here we're moving, you remember EDI is the first argument. So you remember our sum function takes the address of the input array as its argument. So this move, we're moving the address of the array into EDI for the first argument. But the compiler doesn't know what that address is going to be. Right? So it just moves an immediate value of 0 into EDI temporarily. Right? So you can see this is all zeros. The BF is the move instruction, and then there's all zeros for now. And then it places this relocation entry in the relocation section of main.o, and it says to the linker at offset A. So these, let me remind you, these are our main.o module only contains one function. So that function starts at offset 0 in the code section of the module, in the .text section of the module. If there were other functions in this module, they would follow immediately after. Okay, and so you can see what the compiler is. It's just generating offsets of these instructions from the beginning of the .text section, and it includes this relocation entry which says to the linker, hey, when you're relocating main.o, at offset A in this .text section, you've got a reference, a reference to an array in the form of a 32-bit address. Okay, so eventually the linker is going to have to patch up these. So this is address 9. This is address A. It's going to have to patch up the 4 bytes starting at address A with the absolute address of the symbol array. And then similarly, the reference to this function sum, the compiler has no idea where sum actually will end up. It doesn't even know what module it's in, or even if it is defined in a module. So in this case, it just it does a call with all zeros And then it adds this relocation entry that says to the linker, at offset F, you've got a 4-byte PC relative reference to a function, to a symbol called sum. And then this is sort of a arcane detail and it includes, there's an option to include a bias in the offset. And since calls are always resolved using PC relative addressing, the value that's going to be placed here at these 4 bytes at offset F is going to be an offset from the current RIP value, or programmer counter value. And since the program counter always points to the next instruction, it includes this, which is 4 bytes away, it includes this offset of -4. So I talk about it in detail in the book if you really want to know how this works. But just the point here is that there's enough information for the linker to actually fill in the right address. So now if we look at the relocated text section, so if we compile this code into an executable and then we use objdump to disassemble it, then what you see is this reference here where we move the address of A into EDI. Those 4 bytes, which were originally 0, have now been updated with the actual address of array in memory at runtime. Okay, so the linker's decided that the array is going to go at address 0x601018, and then it's actually patched the 4 bytes in the move instruction with that absolute address. And the call to sum it's also been updated, but this one's interesting, right? So the address, it's been updated with the PC relative address of 5. Okay, so when this program runs, this call instruction, what it will do when it computes the absolute address of the function sum, it will take the current value of the program counter, which is the next instruction, so 4004E3, and it will add to it whatever value is in this immediate field, okay, which is you interpret it as a 2's complement integer. So it can be relative, you can go minus or plus. In this case, it's saying that the function that you want to call is at 4004E3 plus 5, which is 4004E8, which is the address of sum. Okay, and so the linker does, the compiler has all the smarts. The compiler computed the relocation entry. The linker is just blindly going through each of those relocation entries and just doing what it's told. Okay, but the net result is that now all of these references have been patched up with valid absolute addresses. Now, once the linker has created an object file, that object file can be loaded, the code and data in that object file can be loaded directly into memory with no further modification. Okay, so if you look at all of the read-only sections in the executable, so there's this init section, which we don't have to worry about that. All the code is in the .text, and things like jump tables are in RO data. All of this data can be loaded directly into memory as is. Okay, so these bytes can just be copied directly into memory, and that that forms a so-called a read-only code segment. The data in the .data and BSSX sections can also be copied directly into memory. Okay. And in the case of the variables in .data, they'll be initialized to a value that's stored in the symbol table. So we're drawing our memory here. This is the address space that every Linux program sees. And we're drawing addresses starting from 0 and going up, increasing as we grow up. And every program is loaded at this same address, 0x400000. And so the code comes directly from the object file. The data comes directly from the object file. And then that's followed by a runtime heap, which is created and managed by malloc. So when you dynamically need to allocate memory, like using malloc, that memory comes out of this heap, which starts immediately following the data segment and grows upwards. The stack is at the very top of the visible memory that's available to application programs. The memory above that is restricted to the kernel. Okay, so if you try to access those memory locations, you'll get a seg fault. And then the stack, as we know, grows down. So this is managed and created at runtime. And then there's this region, somewhere in this huge gap between the stack and the heap, there's a region for shared libraries. So the .so files all get loaded into this memory mapped region for shared libraries. Now the top of the heap is indicated by this global variable maintained by the kernel called break, BRK. And the top of the stack, as we know, is maintained by the general purpose register, RSP. Now there's a little bit of this is a little bit of a simplification. If you actually look at the addresses returned by malloc, there's actually two heaps. There's a heap up here in the high memory that grows down that's used for large objects, very large, if you malloc a whole bunch of space. And then the heap that grows up is reserved for smaller objects. So I'm not really sure why they do this. I think it allows them to have separate allocation algorithms for large objects and small objects. Okay, so one of the real advantages of linking is it allows us to create libraries of things. So it's always something we want to do as programmers. We always want to create abstractions and then present those abstractions to users, right? And we do that by creating libraries, defining an API. Yes?
How much space is allocated for the heap? So how big can the heap grow?
I think it just no. Actually, that's a good question. The things I've done, it just grows until it runs out of memory, right? So I don't think. Actually, that's a really good question. I mean, I've done those experiments, and it eventually reaches some limit. Yeah, I don't know. It's a very large number, but so. As programmers, we always want to abstract, define APIs, package up those APIs, and make them available to other programmers. So how can we actually do that? How can we make commonly used functions available to other programmers? Well, one thing, given what we've learned so far, you could just take all the functions and put them all in a single big C file, right? And then programmers would just link that C file into their programs if they want to use them, right? Another option would be to take, that might get kind of unwieldy if it's a big library, right? libc has hundreds and hundreds of functions. So another option might be to just take each function, put it in a separate file, and then compile them all together, compile and link them all together. So this is more space and time efficient than our first option, but it seems like it would be burdensome on the programmer because the programmer would have to know where all these functions were and put them in make files. It'd just be a lot of, you could end up with a ridiculously large command line to GCC. So the one solution to this problem is that the first solution that the developers of Unix came up with is something called a static library. So the idea with a static library is that you create this archive called a .a file, which is just a collection of .o files where each .o file contains a function. Okay, so you take all the functions in your library, you use option 2 to create a bunch of .o files, and then you use a program called an archiver, AR, to take those .o files, put them together all together in a big file called an archive, with a table of contents at the beginning that tells you the offset of each one of the .o files. Okay? So an archive is just this concatenated collection of .o files. And then you pass that archive to the linker, and it only takes the .o files that are actually referenced and links them into the code. Right? So it's a more efficient way. You can have a huge archive, but like libc, but if you only call printf, the only .o file you get is printf.o. Okay, so the way this works is, as before, we take all the functions we want to put in our library. We run them through our translators to get .o files. We pass those to the archiver to get the archive. So in this case, libc.a, and which has this code for printf that we might want to use. Right? And so we can recreate that archive anytime we want. So if one of these functions changes, like say printf changes, you just re-archive recompile printf, and then re-archive all of the .o files. So in libc, it's about 1,500 object files in its archive. Things like printf, scanf, simple integer math, and there's also a math library, which has several hundred common functions for things like floating point math, sine, cosine, tangent, etc. These libraries, the convention is that a library always is prefixed with lib, this lib, and then sort of some indication of what it does. So now let's see how linking with these static libraries would work. So I've created a little example here. I've created a library called libvector.a, and it consists of functions that manipulate vectors. And this is a real simple library. It just adds, there's a function to add two vectors, x and y, together and return the result in z. And then another similar function that will do pairwise multiplication of two vectors. So xi times yi equals zi. And now I compile these two programs and I'll package them into an archive called libvector.a. And then in my main program, I'm going to call one of those functions addvec to add these two vectors x and y together. So now what happens when we compile this program, we've constructed the archive libvector.a from advec.o and multvec.o. And we pass that archive to the linker along with our main2.o relocatable object file. And we also pass it libc.a, which has the definition of, which contains printf.o, and anything else that printf.o might call. So these three, the linker detects the reference to advec, the function advec, and so it just pulls advec.o out and ignores the rest. Similarly for printf.o. And then it compiles all those main2.o, advec.o, and printf.o all together into this fully linked executable called prog2c for compile time. So we're doing this linking at compile time when we call a GCC. Now, what the linker does when it's using static libraries, it scans all the .o files and .a files in order on the command line. So you're just typing GCC and then a list of .o files and .a files in some order. So during the scan, it keeps a list of the current unresolved references. Right? So if let's say it looks at main.o first and there's a reference to printf, well, that's an unresolved reference because printf's not defined in main.o. So that goes in a list of undefined references. And at some point or another, as each new .o file or .a file is encountered, the linker tries to resolve its list of unresolved references with the symbols that are defined in that .o file or .a file. And then if there's any entries in the list at the end of the scan, then there's an error. Okay? So that the key here is that the linker will try to resolve these references from left to right on the command line. And so this is another sort of important thing for you to know as programmers, because the order that you put your files on the command line actually makes a difference. Okay? So you can get sort of weird, baffling linker errors if you use the wrong order. So for instance, suppose we've got a function, an object module called libtest that calls a function that's defined in libmine.a. Okay, and so these dash L's, dash big L period, that says to look for library files in the current directory. That's what the dot. Look there first, and then look in the normal places that you look. And the dash lowercase l, it's like an abbreviation. We could replace this with just the fully spelled out libmine.a. Okay, but you'll see this lowercase l used a lot. So libtest calls a function that's declared in libmine.a. So the linker looks at the unresolved symbols in libtest.o, and it detects that there's this unresolved function. Let's say it's called foo, or no, it's called libfun. So and it puts it on the list, and then it goes on to the next command line entry, and that's libmine.a, and in there it finds this symbol libfun, and it resolves the reference to that, to libfun, to the actual address, the relocated address. Now, if we switch the order and we put libmine.a first, followed by libtest.o, well, there's no unresolved references in this library, right? It's just a collection of function definitions. So there's no unresolved references, so the linker looks at that. That's all good. And then it looks at libtest.o, and now there's an unresolved reference to libfun, but we're at the end of the command line, so that's a linker error. So you get this really cryptic error message. And if you didn't know about this ordering rule, you wouldn't have any idea how to debug it. Okay, so the static libraries are kind of the old-fashioned solution. The modern solution is to use dynamic libraries or shared libraries. So the reason there's this sort of newer form of libraries is static libraries have some disadvantages. So if you compile with static libraries, then every function that uses printf, or every program that uses printf has to have a copy of printf. Okay, but almost every program uses printf, right? So there's shared libraries provide a mechanism where there can just be one, there's just one instance of a shared library member like printf, and every program running on the system will share that one copy. Okay. So that's sort of the big disadvantage is this potential duplication. So shared libraries are different in the sense that they contain code and data that are linked and loaded into the program not when it's compiled and linked into an executable object file, but actually when the program is loaded into the system. So linking of references to shared library objects is deferred until the program is actually loaded into memory, until the executable object file is actually loaded into memory. And this can it can even happen, it can happen when the program is actually loaded into memory, but it can also happen at runtime, anytime at runtime. So you can be running a program, and that program can arbitrarily decide to load a function that's declared in a shared library. Okay, and I'll show you that. It's really cool. Now these things are often called shared libraries. They're called dynamic link libraries. Like in Windows, they're called DLLs. .so files, they're all reference the same thing. Okay, so this, like I said, the dynamic linking can occur when the program's loaded or after it's loaded and actually running. And there's this sort of big deal that shared library routines can be shared by multiple processes. And we'll look at this. This will make sense when we look at virtual memory, so don't worry about that now. But here's how the process works. So first we have to create, instead of creating an archive, we create a shared library. So our libvector routines, instead of creating an archive, .a file, we create a .so file using the shared argument to GCC. So we take our two input functions, addvec and multvec, and shared says to create, and we're telling GCC to create a shared library and place it in libvector.so. Okay, and there's also the C developers have created a shared library called libc.so that contains printf and other standard library functions. So we take our program, main2, this is the same program that calls addvec, and we compile it into main2.o, and we pass main2.o and these .so files to the linker. Now the linker doesn't, at this point, it doesn't actually copy, let's say we're using addvec or printf, it doesn't actually copy those functions or do anything with them in the executable. It just makes a note in the symbol table that those functions will need to be, the references to those functions will need to be resolved when the program is loaded. Okay, so it puts in a relocation entry that says, fix this up when you load the program. So it's partially linked, but it's not fully linked. You can't take a program, you can't take a executable file that was dynamically linked and load it directly. What you do is the loader, which is the execve system call, and we'll learn more about that, but this is just a syscall that loads executables into memory and runs them. The loader takes the executable, and then it takes the shared .so files that this program needs. Okay, the linker also made a note of which .so files it needs. So the loader calls the dynamic linker, which takes those .so files and then actually resolves all the references to any unresolved reference. Okay, so the address of the addvec and printf functions isn't determined until the program is loaded, and it isn't determined by the dynamic linker until the program is loaded. So the dynamic linker goes through a similar process that the static linker did, sort of fixing up references to addvec, references to printf, and then at that point the binary is in a form that can be executed directly. So, question?
Yeah, I just have a cool question. From before, you said that it scans like your command line argument like in order.
Yes.
But what if you like include a file? Where does that go? Like if you include a file that's like in your same directory, so you don't actually type in the command line.
Okay, the question is, what happens if you include a file? So includes are handled by the C preprocessor. So they're gone. They're long gone by the time the linker gets around to it. Okay, so the C preprocessor just takes # define, # include, and interprets those and outputs another C program. So if you include a file, the C preprocessor just takes that file and just expands it, and the output C program contains an expanded version of all the files that you included. Okay. Now, what's really cool is that you can also do this dynamic linking at runtime. So what I showed you before, we're doing it at load time. But you can also arbitrarily decide to load, link, and call a function from any function defined in a .so file. And the way you do it is there's an interface called the dlopen that's in libc that allows you to do this. And so let's say we want to, this is our main program, and just like before, we want to call addvec. Okay, but addvec now is defined in a .so file, the exact same .so file that we generated before. When we compile, so we'll call this dll.c. When we compile this program, dll.c, we have no idea that it's going to call a function from libvector.so. We just compile it as though it was a standalone C program. Within this program, though, we declare a function pointer called addvec, and we give the prototype for this function. It's pointers, so it's 2 input arrays, the output array, and the size. And then first we dynamically load the shared library that contains the function we want. So we call dlopen, and we say load up this .so file into memory so that I can call a function. But don't worry about resolving the references to functions until I actually tell you to. That's the lazy part. And so what this dlopen returns a handle that then you use in subsequent calls. Okay. So if the handle is null, there was some kind of error, like maybe this .so file doesn't exist. So once we've opened that .so file, then we use dlsym with the handle. So this, and then we give it we pass as a string the name of the function that we want to invoke. And what we get back from dlsym is a pointer to that function. And then we we can use that function just like any other function. So we can use that function pointer, and we will call it just as though it were a statically defined function. So you can see this is a very powerful technique. Right? Okay, so let's finish the last little bits of the class. I want to show you to try to convince you that linking is actually interesting, which is kind of a hard sell sometimes. Yes, question?
So you said add track would be a function pointer.
Yes.
So wouldn't it need to be referenced towards a blank
No, that's how, no, you just, it's declared as a function pointer, and then you just use the name of the function. You don't have to dereference it. Or you call the function by just using that function pointer name. Okay, just like I did. If you dereference it, you just get back a pointer value. You'd get back the address of that function. All right, so it's kind of a hard sell to convince you that linking is interesting, but I'm going to try. Okay, so there's this powerful technique called library interpositioning, and the goal is to intercept function calls from libraries and do something, intercept them for some reason. Right? So what we typically want to do is intercept a function call, maybe record some statistics or do some error checking, and then call the real function as intended. Right? So the idea is we're going to create wrappers, and when a program calls a function, what we're going to do is we're going to execute its wrapper instead. Okay? And we're going to do it without changing any of the source. Right? Now, there's a lot of reasons, there's a lot of applications for this. The neatest one that I know is that these Facebook engineers were trying to deal with this year-long bug in the Facebook iPhone app, and nobody could figure out what was going on. And they figured it out using library interpositioning. They figured out that there was something in the network stack writing to the wrong location, and they figured it out by intercepting all the calls from their Facebook app that did writes. So things like write, write-v, p-write. So they intercepted all those calls, and then they were able to, when they looked at the arguments and how those functions were being called, they determined the error. You can also use it for monitoring and profiling. Like, so if you want to know like how many times different functions get called, you can interpose. We use it for generating address traces. So your malloc, when you do your malloc lab later in the semester, you're going to be evaluating your malloc using traces that we generated from real programs using this interpositioning technique. Right? So we interposed on all the malloc and free calls in like Netscape. And then we just recorded what addresses and sizes malloc was returning and what blocks free was freeing up. And we just created a trace of those. And then, so let me show you how you would do this. So the idea, let's say we have this main program, and the idea is to trace all the malloc and free calls. So there's one malloc call and there's one free call. And we want to know what these addresses are, and we want to know what these sizes are. So we can do this at either compile time, link time, or run time. To do it at compile time, we first write wrapper functions called mymalloc and myfree, where mymalloc calls the real malloc function, and then it prints out the size that it was called and the address that malloc returned. Okay, so this, when we run our program, it'll print out all these addresses, and it does the same thing for free. And then here's the trick. In malloc.h, we define malloc to be mymalloc, okay, and free to be myfree. and then we give the prototype for it so the compiler doesn't get confused. And then we compile mymalloc.c into a .o file, and then we call our program, which is our main program, int.c, for interpositioning. And we call that, and here's the trick. We call it with the dash cap I argument, and we say, look for any include files in the current directory. Okay, so this was similar to that L dash cap L argument. But because we tell GCC to look in the current directory first, so this is sort of where the interpositioning happens. Because when it does that, it's going to find a library called malloc.h. I mean, a .h file called malloc.h. And so all the calls to malloc will be translated by the C preprocessor to mymalloc. So when we run this, it prints out the malloc and free trace. Now we can also do this at link time. So we can tell, see, in order to do this, we had to get access to we had to compile the program. We didn't have to change it, but we had to compile it. We can use link time interpositioning to avoid that compilation. So the way this works, we define our wrapper functions with this special name __wrap malloc. And this calls the real malloc function and then prints out the information. And then at link time, then we do the interpositioning by calling the linker with this special -WL argument. And so what this does, the -WL flag to GCC says, hey, take what follows, the argument that follows, replace all the commas with spaces, and then invoke the linker with this argument. Okay, so what we're doing is passing arguments to the linker. And this --wrap argument to the linker, it tells the linker to resolve all references to malloc as __wrap malloc, and all references to _real malloc should be resolved as malloc. Okay, so anywhere in the program where we call malloc, it'll be resolved to __wrap malloc, and it'll invoke our wrapper. And then the wrapper calls real malloc, which because of this flag resolves to the actual malloc routine. Now here you can also, and the really amazing thing is you can also do this interpositioning at load time and runtime when the program's loaded. So you don't even need access to the .o files. All you need is access to the executable. Right? And for every program we have access to the executable. So think about that. We can take any program and we can interpose on its library calls at runtime. So the way we do this is we write the wrapper function now uses the dlsim call that we saw before. And we call it with this special function, this special argument called next. And what this is saying is get the address of the real malloc. Okay, so, and we're going to trick the linker into looking first to our implementation of malloc. But here we want the real one. So we're telling it to look in the next place, its next place that it would normally look, and fetch the address of malloc. So the result is a pointer, a function pointer called malloc_p, and then we can just call that function to call the libc malloc, and then print out the data. Okay, we do the same thing for free. We use dlsim in exactly the same way for free. And then the interpositioning now happens when the program is loaded. So notice, we build our main program now, int r for runtime interpositioning. We built it, we created our .so file, mymalloc.so, using the shared argument. And then we compiled int.c into this executable called intar. But notice there's no mention of mymalloc.so anywhere. And now the interpositioning happens when we actually run the program. And we do it, we affect the interpositioning by setting an environment variable called LD preload to mymalloc.so. And so this is an environment variable that tells the dynamic linker to look first in the value of LD preload is a list of locations. Look first in those locations to resolve references, and only later look in the normal system places. So we're saying to look in mymalloc.so for unresolved references first, and then we're invoking. So this is in Bash, this is how you initialize an environment variable. So we're initializing it to mymalloc.so, and then we're loading and running the program. And so all the references to malloc get turned into the references to the wrapper function, the malloc function that we defined in our program. Okay, so that's it. So that interpositioning is a really cool technique, and it's only possible because of linkers. So, all right, so good. We'll see you on Thursday, and good luck with your cache labs.